Before we can really dive into our topic of waves, it's important for us to have a solid understanding of vibration. So in this video, we're going to look at this system, which is a mass on a spring as it vibrates back and forth. This is undergoing a particular type of motion that we call simple harmonic motion. So we're going to look at this quite a bit in this particular video, but we'll also talk about other types of vibrations as well. So if you think of like a bobblehead, what sorts of words might you use to describe this motion of the bobblehead or this mass on a spring? Well, you might think of things like oscillating. It's oscillating, it's going back and forth, it's repeating, and there's a variety of other words that you might use to describe this. In this particular lesson, we're going to look at ways to quantify this motion, but also ways to graph it to show how it's responding as it's moving back and forth, up and down. All right, so let's look at this example here. I've got it modeled out here in an animation. If I let this come to a rest here and let it just sit there, we say that this is in its equilibrium position. Is, to be fair, not the perfect equilibrium of the spring itself, but under the weight of this mass, it's where it's coming to a rest. So we're going to say that that is the equilibrium position for this system. If I pull this down, this is now at its minimum position. And then if I release, I see that it's vibrating back and forth. If I release it here, it's vibrating back and forth between this minimum and this maximum position. They are equidistant from that equilibrium position, so they're just vibrating back and forth across that equilibrium. When it's doing this, when it's oscillating around an equilibrium position, we call this simple harmonic motion. And there are a variety of different examples of this. This is a really simple example that we'll use throughout this video coming back to. So let's look at this again, only instead of looking at its position, its displacement, let's look at the forces that are at play. If I pull this down, there is going to be a force that's trying to restore it back to its original position, back to its equilibrium. Because if I release it, I see that that's the direction it starts accelerating. So let's watch what happens here with this force. We're going to call this the overall net force once I release. And as it goes up, notice that the net force changes its direction depending on where the position of the mass is. We call this the equilibrium, or the restoring force, because it's always trying to restore its position back to the equilibrium. So if it's pulled downward here, it's going to have a restoring force pulling up towards the equilibrium. If I actually give it a displacement upward, it's going to have a restoring force going down, which isn't too crazy to think about. It's something that probably you would be able to guess. If we look at the sign convention here, it's important that we're looking at positives and negatives, especially when we start getting into other properties as well. So let's define an upward restoring force being a positive force and a downward restoring force being a negative force. It could be flipped. As long as you're consistent, you'll be okay. So if we say that pulling down gives us a positive restoring force, another way that we can describe that is this is a downward displacement, which means that I'm displacing it in the negative direction. So a negative displacement here gives me a positive force, and a positive displacement gives me an overall negative net force. Now, this can be predicted actually using an equation that we saw earlier in our year, this idea of Hooke's law. We saw this in terms of elastic energy, and Hooke's law states that the force of a spring is equal to some constant times the displacement, the stretch of the spring. Well, something that we didn't look at before as much, we didn't focus on it at all, is this negative here. This negative is actually important because it tells you that the force is opposite the displacement, which, until you think about a model like this, is kind of confusing. But here, if I pull downward, I give it a negative displacement, it's going to result in a positive force. That the force is just in the opposite direction of the displacement. Another thing that's important to note about this is the acceleration will always be in the same direction as the force. So if I pull it down, give it a negative displacement, its positive net force results in a positive acceleration. It accelerates upward. Likewise, if I give it a positive displacement, its negative net force gives it a negative acceleration to accelerate it downward. So we can see that a negative force results in a negative acceleration, positive force, and positive acceleration. F equals ma. So you'll notice a negative sign every time we're talking about this. Well, something that the IB curriculum likes to talk about every once in a while, or give you a question about, is in terms of this statement here. Acceleration is proportional to the opposite of displacement. So that means two things here. It means that it's proportional, that if I pull it farther, it means it's going to accelerate faster, because there's more force the farther I stretch it. It also means that it accelerates in the opposite direction of the displacement. A way that this is sometimes symbolically shown is it says a and then this funny symbol here, negative x. This funny symbol you may have seen in a math class before. That actually represents a proportional to. So that states that a is proportional to negative x, which is the opposite of whatever x is. That negative just flips the sign, which means that if I give it a negative displacement, negative that will be a positive acceleration. You just flip the sign. So let's look at this one more time with both force and acceleration. And while you're watching this, think about when the force is the largest, when is the acceleration the largest, and when is the velocity the largest. So I am displaying there the force and the acceleration. You can see where the magnitude of that is the largest, but also look at the velocity. You might notice there that at the extremes, the force and the acceleration are both very large, but the velocity is nothing. As it's vibrating up and down, at the extremes, as it's turning around, it actually comes to a rest for a very, very short period of time. That is the slowest it moves, and then as it crosses the center, it's crossing as fast as it could be going. So, looking at this, we can summarize that in a where is the greatest sort of table here. So if I want to find where the greatest displacement is, well, that's where it's farthest away from its equilibrium. We're going to say that if we're going to label these A, B, and C, that A and C are the farthest from the equilibrium. B is the equilibrium. That, by definition, is zero displacement. Now, we also know that the farther we get away, the higher the force is, and the higher the force is, the higher the acceleration. So it goes to show that if we have a high displacement, we have a high acceleration. The displacement and the acceleration are opposite each other, but their magnitudes map out proportionally. Now, this velocity is the tricky one. The velocity at A and C are exactly zero. That's where it comes to a stop at the extremes. It's B, it's this middle part here that has the highest velocity. So the next natural thing to do is, can we graph this over time? Watching this happen is nice, but that doesn't translate very well to just a static piece of paper or any sort of problem. So here, if I pull this down, if I load it, and then start a graph as soon as I started moving, this graph that's created should represent something that feels like a fairly familiar shape. It's this nice sinusoidal shaped graph. This displacement over time is showing where it is relative to the equilibrium. Is it above or is it below that equilibrium line? Now we can plot this out here, making note of where this A, B, and C position is. So starting out at A, if I were to release it, it goes up to B, then C, B, back down, and so on. And that would continue forever and ever, as long as it's not damped too strongly to come to a rest. Now, if I want to translate this to these other graphs down below, I need to remember some of the things that we did in our motion graphing earlier on this year. Now, you can see here this displacement graph has both a positive displacement and a negative displacement. Velocity and acceleration both have positives and negatives as well. All of these are vector quantities. So if I want to find the velocity, I need to know the slope of my displacement versus time. Well, there's a couple spots here that's pretty easy to find. That A is a slope of 0. So I'm going to plot out A at that position is a velocity of 0. C is also a slope of 0. So that velocity is 0. We actually talked about this earlier, that the velocity at these extremes is 0. The highest and the lowest point, the minimum and the maximum, are both a velocity of 0. Now, B here has a velocity that matches the slope. So a positive slope will track to a positive velocity. And notice here that is the steepest slope, so that is the fastest it's going. And then a negative slope here at this B gives us a negative velocity. Now, it's not a mistake that B shows up twice. It crosses that center twice in its full cycle. It's going up and going down. So we have a positive velocity and a negative velocity. And I can connect all of those dots using another sinusoidal shaped graph as is plotting through those. Now, if I want to find an acceleration versus time graph, I need to know the slope of my velocity versus time, because acceleration is just the rate of change of velocity. So looking for my easy spots here, I've got a leveling off here at B. That is a slope of 0, so the acceleration is 0 at that point. B again is a slope of 0, acceleration of 0. It's actually not accelerating at all as it passes in the center, which is kind of weird. That acceleration is just flipping its sign. So A has a very positive acceleration, positive slope, and C has a negative slope. So we plot that as a negative acceleration, and we can see that that graph shows up here. Now, looking at these three different graphs, it's easy to become dizzy just trying to look through all these different examples. And it's very important to note that the graph isn't always going to look exactly like this, because I could have started this at any point along the way. I could have even started in the middle and just given it a little pulse, a force to push it up or down. So it's important to know how these graphs are related to each other, not memorizing the graphs themselves. A good way to check to see if you've done this correctly is to look at one other scenario that we talked about with acceleration and how it's related to displacement. Is we know that the acceleration is always opposite of displacement. A is proportional to negative x, which means that if I take my displacement and my acceleration and overlay them, they are always opposite graphs. That when the displacement is negative, the acceleration is positive, and vice versa. Okay, velocity is the weird one. It does not relate it in that way. Look at your slope of the displacement graph in order to find your velocity. All right, so if we know the velocity, we know the position, we can figure out some energy scenarios for the simple harmonic motion as well. If we look at the displacement versus our potential energy graphs, if I wanted to plot out how much potential energy this has throughout its entire motion, I need to know its position, because potential energy is related to its position. Something that's different about potential energy and displacement, though, is potential energy is a scalar quantity and displacement is a vector, which means that potential energy can never be negative, whereas displacement can. So all we're looking at is the magnitude here. When the displacement is 0, so is my potential energy. That right now, at the very middle, there is no potential energy. It's at its equilibrium point. But when my displacement is as far away from the equilibrium as possible, I result in a very positive potential energy. If I look at the same scenario in terms of a velocity graph and a kinetic energy, I can see a plot that looks something like this. And the relationship is very similar here as well, that when the velocity is 0, I have no kinetic energy. So that looks like that. But notice that the other parts of this are different, because kinetic energy, just like potential, is a scalar quantity. So it will always be positive. That it doesn't matter if your velocity is positive or negative, it's always going to give you a positive kinetic energy. So where the velocity is the highest magnitude, regardless of its direction, you will have the highest kinetic energy. Plotting this all together, you see this really beautiful graph. What I want to note, though, is if you were to add up the potential and the kinetic energy, you're going to get a straight line. That your total energy is always the same. It's always the sum of these. So it's just swapping between potential and kinetic throughout that entire motion. All right, now I want to look at two graphs that are the weirdest graphs that you're probably going to see all year. And that's an acceleration versus displacement and a velocity versus displacement graph. So note here, our x-axis is no longer time, it's displacement. So let's plot out based on this picture of what that looks like. That B is my equilibrium. That's a displacement of 0. A, we're going to say, is a negative displacement. So we're going to put that on the negative part of the axes for displacement. And C is a positive displacement. So we're going to plot that out here. So that gives us kind of this roadmap along the way. If I know that acceleration that's pointing up is a positive acceleration, loading this by pulling it down is going to result, when I release, in a positive acceleration to begin with, which means that at position A, a negative displacement, I'm going to have a positive acceleration. If I let this release and I spring it up to the top, I notice that at the top my acceleration is negative, is pointing downward. So I have a negative acceleration when my displacement is positive at position C. If I let this continue, notice that it just oscillates back and forth between those two positions. So my graph that becomes visible is just this diagonal line that is showing me a direct relationship, just inverse. So inverted in the fact that it's as a positive displacement gives me a negative acceleration and vice versa. But at zero displacement, zero acceleration. The next graph that I want to look at is a velocity versus displacement graph. So I've plotted in for the displacement the same three positions, that a negative displacement is A, positive is C, just so we can see it in this picture. If I load this up, pull it down to the bottom, that velocity is zero. The moment I release is not going to have any velocity at all. So I can plot that on here as zero velocity. The y-axis is zero when the x-axis is A. Then if I release, it speeds up and then slows down to get to C. We'll look at that one more time. And now pay attention to the graph. As it goes from A to C, you'll notice that the velocity gets big and then small again. All right, if I now release it from C, we'll see that the velocity gets negative, speeding up and then slowing down to a stop. Let's look at that one more time. Looking at the graph, going from C to A, it gets a very negative velocity as it's crossing B. So what results is a graph that looks like it breaks our rules of math. That this function, it's not really a function, is kind of going around in this circle. That B could either be a positive or a negative velocity, depending on the direction that it's going. Is it going up or is it going down at that point in time? A and C will always have a velocity of zero because it's at the maximum, but B will either be going up at a high velocity or down at a very negative velocity. You need to know these two velocity and acceleration versus displacement graphs. They're weird ones. IB loves to ask about them. All right, the last piece here that I want to talk about today is how you time this. If this is oscillating back and forth, how do you figure out and quantify how fast it's going? Well, the best way to do that is to time how long it takes to make one full cycle. So here, if I start at A, I time how long it takes to go up to C and then back down to A. All right, that we're going to call the period. That's the period of this cycle, that it goes up, back down. It's very similar to the period that we talked about in circular motion, the time for one complete cycle. An easy thing to do by accident is to measure, like if it starts in the center here, measure the time it takes to get back to the center. It needs to go to both maximum positions. So here, if I were to time to go down and then back to the center, that is not the period. That's only half the period. The full period would be down, back, up, and then back to the center. So the way this looks in a graph is we can look at the peak to peak or trough to trough, but the period is the time per cycle. We use this symbol capital T, just like we did in our circular motion unit, and our unit is seconds. Another way that you can time a graph, or time simple harmonic motion, is by counting how many times it happens per given unit time. So cycles per second would be our frequency. We're going to use the symbol for frequency, this italic F. And then our unit is hertz. So 5 hertz would be 5 waves per second, or 5 cycles per second, 5 full revolutions per second. Period and frequency are related to each other. They're inverse quantities. The period is just 1 divided by the frequency. So if you know how many seconds for one wave, you can figure out how many waves for every 1 second. This equation is given to you in your data booklet. You can also think of it not only as T, the period is 1 over F, but f, the frequency, is 1 over the period. We can look at this in terms of a couple example problems. Taylor Swift's song Shake It Off has a tempo of 160 beats per minute, so 2.67 hertz. So 2.67 beats every second. How many seconds are in between the beats? So if you were to snap along to that groovy tune, you can figure out the time between snaps. Well, it's as simple as saying t is equal to 1 over f. 1 over 2.67 is 0.37 seconds. It should make sense. If there's almost 2.5 beats per second, you can imagine that the time between beats is less than a second. Likewise, if you're standing on the beach with your feet in the water and notice that a new wave comes crashing every 4 seconds, what's the frequency of the waves? Well, 4 seconds, that's your period. That's the time for one complete wave. So to find the frequency, it's just 1 divided by 4, which is 0.25 hertz, which is saying that you experience a quarter of a wave every second if you're standing on that beach. All right, one final problem that's a little bit harder. It's if you're pushing your younger brother on a swing, you end up pushing 12 times in a minute. What's the period and frequency of that swing? Well, 12 times per minute is going to help you figure out ultimately the frequency and the period. First, if I want to find the frequency, I need to know the period. The period is just time per swing. So 60 seconds in a minute and 12 times in that minute, which means that every swing took a full 5 seconds, which means that the period is 5. If I want to find the frequency, 1 divided by 5 is 0.2 hertz. So 0.2 swings every second. In this lesson, we talked about relating acceleration of an object in simple harmonic motion to its position, as well as its force and its velocity. You can graph the displacement, velocity, and acceleration versus time. Very important to be able to create those sinusoidal graphs. And you should be able to describe and relate the properties of period and frequency, as well as being able to calculate the period and frequency from a given scenario.